Hey everyone, welcome back to The Explainer. So, if you're the kind of person who just has to know exactly how things work under the hood, you are absolutely in the right place today. We're going to take a pretty standard code review and turn it into a full-blown algorithm story. We're looking at this super specific, but honestly fascinating problem, taking text in one format and transforming it to another, but doing it while strictly adhering to a pretty ruthless set of rules. So let's just dive right in and decode the CamelToSnakeCase function.
All right, let's start with a bit of a conceptual challenge here. When you or I read a string of text that has mixed capitalization, our human brains just instantly recognize those capital letters as the start of new words, right? We naturally see the bumps in the word. But a machine, well, a machine just sees this endless continuous stream of bytes. So how do you actually teach a computer to spot those hidden boundaries, isolate them, and transform them, all without completely wrecking the original data? Well, that is the exact puzzle this function is solving.
Just to get us all on exactly the same page, let's look at the two contenders here. On one side, we've got upper camel case, where the words are just smashed together and they're only separated by those capitalized humps. And on the other side, lower underscore snake case. This is where everything is lowercase and words are explicitly linked up by underscores. Our mission in this explainer is to really unpack the Go code that perfectly bridges the gap between these two very different casing styles, and we're going to see how it carefully dodges some pretty tricky traps along the way. Okay, so here's our roadmap for the breakdown. 1. The shape-shifting string problem. 2. First checkpoints and validation. 3. Looping with future sight. 4. The snake case rules. And 5. Tracing the decision tree. All right, part 1. The shape-shifting string problem. So I want you to try and picture this function not just as, a block of text on a screen, but almost like a physical high-security funnel. Data gets dropped in at the top, and it is just ruthlessly filtered, analyzed, and shifted around until only perfectly formatted data drops out of the bottom. This right here is the complete Go function for CamelToSnakeCase. Now, don't panic. You don't need to read every single line right this second. We're going to break it all down. But at a high level, the mission here is to parse an incoming string, literally character by character, dynamically build a brand new string, and apply our specific formatting rules. It's basically a highly meticulous inspector.
And right at the very top of that funnel, we hit what developers love to call a fast fail mechanism. Look at this. If the incoming string is perfectly empty, the function just immediately returns an empty string. I mean, why burn processing power running loops and running checks on literally nothing, right? It just bounces empty strings straight out of the funnel before the real work even starts. It's simple, it's elegant, and it's incredibly efficient. Moving on to part 2, first checkpoints and validation. Okay, so assuming our string actually has some data in it, it now hits this extremely strict security layer. Inside our loop, this very first logic block is brilliantly illustrating our primary checkpoint. It's checking if the current character is strictly a letter, and we're talking pure ASCII values here. The condition checks if the character is between lowercase a and z or uppercase a and z. But notice that little exclamation point right at the start? That actually negates the whole entire statement. So it's essentially asking, wait, is this character not a letter? Honestly, you can just think of this logic as a ridiculously strict bouncer at the door of an exclusive club. And let me tell you, this bouncer takes 0 bribes from digits, punctuations, spaces, or any special symbols whatsoever. If he spots even a single non-letter character anywhere in that text, boom, validation fails instantly. The function just stops dead in its tracks and hands you back your original, totally unchanged string. Strict inputs make for predictable outputs, and this bouncer does not mess around. Which brings us to part 3, looping with future sight. Let's look at how this builds into the actual core engine of the code. To process the text, the function uses your standard for loop, iterating from index 0 right up to the length of the string. But take a look at the specific syntax choice happening here. We are iterating strictly by the integer index I, instead of using a standard Go range loop, which, let's be honest, is usually a lot more common when you're dealing with strings. So why go with this manual index approach? Well, it gives us something really cool, future sight. See, when you control that exact numeric index I, you hold the power to actually peek ahead in the string. You can look at I+1 to see exactly what character is coming next, long before the loop actually reaches it. And as we're about to see, this future sight ability isn't just a neat trick. It is an absolute superpower that's completely required for catching some really sneaky edge cases. All right, part 4, the snake case rules.
Now we are at the real heart of the algorithm. This is where the actual transformation happens, or where it gets completely rejected. Let's just deliberately slow the pace down for a second and look at these compound if statements. Once we know for a fact we have a valid letter, we check. Okay, is this character an uppercase letter? And is the index greater than 0? Now we explicitly skip the very first character because a perfectly valid upper camel case string is totally allowed to start with a capital letter, and we obviously don't want an underscore right at the very front of our new string.
So if it is an uppercase letter and it's not the first character, we have to apply the final set of rules before we drop that underscore in. And this is exactly where we use our future site. We ask, is this uppercase letter sitting at the very end of the string, or is the next character also an uppercase letter? Because if either of those is true, it means the string is breaking standard camel case rules, like having a random trailing capital or two capitals just jammed together. If it breaks those rules, we instantly invalidate the string and just return the original. It's only if it passes absolutely all of these checks that we finally insert the underscore.
So the really crucial takeaway here is this decision tree. This maps out exactly how a single character navigates these logic gates. First off, is it a letter? Next, is it uppercase and not the first character? Then, does it actually pass the trailing and consecutive capital checks? Literally every single byte of our string has to navigate this maze to either earn its underscore, pass through unchanged, or crash the whole entire process. And finally, part 5, tracing the decision tree. To really lock this all in, let's actually push some real data through the funnel and prove that this logic holds up. Let's trace a VIP string, hello world, with a capital H and a capital W. At index 0, the H is uppercase. But hey, it's the first character, so it skips the underscore rule. We just add the H. Then the lowercase letters flow through nice and easy. But then we hit index 5, the W. It's uppercase. It's not the first character, it's not the last character, and our future site peeks ahead and sees the next character as a lowercase o. It is perfectly valid. So the algorithm safely drops in an underscore, then the W, and our result is a beautifully formatted hello underscore world.
But we've got to contrast that success with a total failure. Look at the string hey2. The H, the E, and the Y are all lowercase letters. They pass the checks, they get added to our temporary string, no problem. But then at index 3, we hit the digit 2, and instantly that very first bouncer checkpoint wakes up. A 2 is not a letter. The validation is triggered, the entire operation is aborted right then and there, and the function just hands back the original string hey2 completely untouched.
Now, what's really fascinating to see here is how all these weird little edge cases are just perfectly neutralized by the code. Empty strings, strings with random numbers in them, consecutive capitals like an all-caps camel, or trailing capitals like case with a capital E at the end, they are all safely caught and handled. And in the real world of coding, catching these exact types of edge cases is precisely what stops your wider applications from breaking, crashing, or, writing corrupted data to your database. It's just incredibly elegant defensive programming.
Which kind of leaves us with something pretty important to think about. We've seen just how meticulously this function guards its output. But I want to ask you, what actually happens if your application's validation checkpoint fails to catch just a single hidden edge case? Because in the world of software, one unhandled character can literally bring down an entire system. The logic we explored today, it really isn't just about formatting underscores. It's about the relentless pursuit of data integrity. So definitely keep that in mind the next time you're writing what seems like a simple validation check. Thanks for hanging out with me for this explainer, and I'll catch you in the next one.